Hello guys, we're gonna continue with section 1.7, linear independence. So in the previous section 1.5, we studied that homogeneous equations from different perspectives, right? By writing them as a vector equations. In this way, the focus shifts from unknown solution of a times x equals 0 to the vectors that appear in the vector equation, correct? Let's consider the example. So it is already in the vector form. So x1 times 1, 2, 3 plus x2 times 4, 5, 6 plus x3 times 2, 1, 0 equals to 0, 0, 0 vector, correct? So this equation has a trivial solution, of course, right? Let's make it our variables x1, x2, x3 zeros. Then our both sides coincides, which means that both of them are equal, correct? As in the section 1.5, the main issue is whether the trivial solution is the only one. So we are like finding, we want to answer, is it the only one? So basically that's it. And in this section, we're going to introduce two new definitions called linear independence and linear dependency. Okay, so an indexed set of vectors, like for example, x1, v1, v2, v3, and so on, vp in Rn is said to be linear independent if the vector equation x1 times v1 plus x2 times v2 plus dot 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 plus vp times xp equals to 0 has only trivial solution. Okay, what does it mean? You already know trivial solution. So basically when our solution equals to 0, correct? The same set v1, v2, v3, and so on, vp is said to be linear dependent if there exist weights c1, c2, c3, and so on, cp, not all 0, such that the linear combinations of c1, for example, c1 v1 plus c2 c2 v2 and so on, cp vp equals 0. So basically, to make it short, in a linear independent situation, you have a only trivial solution, right? When your solution equals to 0. However, in linear dependency, you have some weights are not equal to 0, not all equal to 0, okay? This is the main difference between them. Equation 2 is called linear dependency relation among v1 and so on vp, our set of vectors, right? When the weights are not all 0. I already said it, correct? Now let's consider the example. So let v1 equals to this vector, v2 equal to this vector, and v3 equals to this vector, correct? Determine if the set v1, v2, v3 is linear independent, and if possible, find linear dependence relation among our vectors. So basically, what we're gonna do is let's use our augmented matrix and construct it, right? So basically we write here is v1 vector, v2, v3, and our solution 0, 0, 0, correct? So what we're gonna do as always, we need to reduce it to echelon form. So we got matrix 1, 4, 2, 0, 0, minus 3, minus 3, 0, and zeros on the third row, correct? Now, let's investigate. So we have one pivot, two pivot, however, we don't have a pivot here. I mean, the pivot equals to 0, correct? So what does it mean? It means that you have two basic variables, x1 and x2, correct? And your x3 variable is going to be free. And each non-zero value of x3 determines a non-trivial solution of 1, correct? Hence, our vectors v1, v2, v3 are linear dependent and not linear independent, okay? Basically, so if you have a free variable, it means dependency. And second, to find a linear dependence relation among our vectors, completely row reduce the augmented matrix and write the new system. Okay, so Here it is somehow reduced, but we are not done yet, correct? To get row reduced echelon form, we need to further use our pivot and make it 0 here. I already discussed in the class, right, how to do it. So after you do it, you're gonna get 0. By the way, don't forget to divide everything by -3 in the second row, okay? So 0, sorry, 1, 0, -2, 0, 0, 1, 1, 0, 0, 0, 0, 0, correct? Let's rewrite our matrix in the form of linear equations. So we have x1 minus 2 x3 equals 0, x2 plus x3 equals 0, and 0 equals 0. So from here, you just express x1 and x2 in terms of x3. So we say x1 equals 2x3, x2 equals minus x3, and x3 is free variable, like we did in the previous section and in the class, right? So choose any non-zero value for x3. Let's take it 5. Then our x1 is going to be 2 times 5 is 10, and x2 is going to be minus 5, correct? Substitute these values into equation 1. Where is 1? So it's going to be here, correct? Yeah, so we're going to get 10v1 minus 5v2 plus 5v3 equals 0. This is 1 of infinitely many possible linear dependence relation among our vectors v1, v2, and v3. So this is very important, guys. Okay. Now let's consider linear dependence of matrix columns. So suppose that we begin with a matrix A equals A1, A2, dot, 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 AN instead of set of vectors. The matrix equation A times X equals 0 can be written in the following form. So linear combination of X and A equals 0, right? X1, A1 plus X2, A2, and so on. Xn, An equals 0. Each linear dependence relation among the columns of A corresponds to a non-trivial solution of A times X equals 0. Thus, we have the following important fact. So basically, the columns of matrix A are said to be linear independent if and only if the equation A times X equals 0 has only trivial solution. Okay? This is very important. If and only if the equation A times X equals 0 has only the trivial solution. For example, determine if the columns of A are linear independent. So what we're gonna do, let's create augmented matrix uh, of this form A times X equals 0. We already created, and row reduce the augmented matrix. Okay. About row reduction, you already know by this point, so we're gonna jump straight to the solution. So we get the augmented matrix in the form 1, 2, minus 1, 0, 0, 1, 4, 0, 0, 0, 13, 0, correct? So at this point, it's clear that there are 3 basic variables and no free variables, correct? So in this case, not to confuse yourself, just divide everything by 13, you're gonna get 1 equals 0. I mean 1 and 0, correct? So the equation A times X equals 0 has only the trivial solution, and the column of A are linearly independent, okay? So basically, you have a pivot in every row, correct? Therefore, there is no way that you're gonna get a free variables. Therefore, your columns of a matrix are said to be linearly independent. Okay. Always, please try to make a consequence. Okay. I'm sorry. Make a sequence of logic. So now let's discuss about sets of 1 or 2 vectors. Okay. A set containing only one vector, say v, is linear independent if only if v is not a zero vector. Okay. This is because the vector equation x1 times v equals 0 has only trivial solution when v, our vector, not equal to 0. The 0 vector is linear dependent because x1 times 0 equals 0 has many non-trivial solutions. Oh, this is obvious, right? Now let's consider the following example. Determine if the following set of vectors are linear independent. So we have two vectors v1 and v2. And here's the same v1 and v2 but with different values. What we're gonna notice from here, I mentioned it in the class. So if you can see, v1 is 2 times less than a v2 vector, right? So notice that v2 is a multiple of v1, namely v2 equals 2v1, correct? Hence, minus 2v1 plus v2 equals 0, which shows that it is linearly dependent because this is a multiple of each other, correct? In second example, the vector v1 and v2 are certainly not multiples of each other, right? There is no way that you can multiply v1 and get v2. Could they be linearly dependent? Now we have to answer. Suppose we take c and d to satisfy the following equations. C times v1 plus d times v2 equals 0, correct? If c is not equal to 0, then we can solve for v1 in terms of v2. Well, this is obvious, right? And we write v1 equals, so move this one to other side, and we're gonna get, and divide by everything by c. So we're gonna get v1 equals minus d over c times v2. This result is impossible. Why is it impossible? Because v1 is not a multiple of v2, correct? So c must be 0. And this is true for d as well. Just do the same manipulation with d. And we can also must be 0. So our set v1 and v2 is said to be linearly independent set. Okay. Now let's study the following definition. A set of two vectors v1 and v2 is linearly independent if at least one of the vectors is multiple of each other. Okay. When it's multiple of each other, it creates dependency. The set of linearly independent if and only if neither of the vectors is a multiple of each other. So this is a very important fact. Okay. Please try to memorize it. So theorem, by the way, in this course I'm gonna give you some theorems, but try to understand what does it say without like formal proof or anything like that. This is not a class designed to learn how to prove, okay? Just try to memorize the fact. So theorem 7, characterization of linearly dependent set. An index set S, which consists of vectors v1 and vp, of two or more vectors is said to be linearly dependent if and only if at least one of the vectors in in S is linear combination of others. Okay. In fact, if S is linearly dependent and v1 not equal to 0, then some vj, like v with the index j, where j greater than 1, is linearly dependent, linear combination of the preceding vectors. Okay. This is very easy to understand, easy to remember. And the following theorem. If a set contains more vectors than there are entries in each row, then the set is linearly dependent. Okay? That is, any set v1, v2, and so on vp in Rn is linearly dependent if p greater than n. So what does it mean? It means p, it is set number of vectors, okay, like v1, v2, v3, and so on. N is number of rows. So in the case when we have p greater than n, we're gonna get what? Linear dependent. Let's consider example 5. Vectors 2, 1, 4 minus 1, minus 2, 2 are linearly dependent. Why? Let's look theorem number 8, and we conclude that because there are three vectors in a set, and there are only two entries in each row. Okay, sorry, in each vector. Indeed, we have 1, 2, 3 vectors, and we have only two rows, right? Therefore, it creates linear dependency. Theorem number 9. If a set S with the vectors v1 dot 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 vp in Rn contains the zero vector, then the set is linearly dependent. Okay, this is like a third indication of linear dependency. Now let's consider example number 6. So just look number B. So we have a vector which contains 0, 0, 0, and it says if our set contains zero vector, then the set is linearly dependent. So indeed, this is linear dependent. And this one is also linear dependent. Why? Because we have 1, 2, 3, 4 vectors, correct? But we only have 3 rows in each vector. That's why it creates, do you remember I told you about this one? P greater than N. That's why we have linear dependent. What about C? Compare the corresponding entries of two rows. The second vector seems to be minus 3 over 2 times the first vector. Indeed, this relation holds for the first 3 pairs of entries, but fails for the fourth pair. So this one is, the last row is does not satisfy, right? Thus, neither of the vector is multiple of each other, and hence they are linearly independent. Okay. So basically, that's it. Now let's consider example. The first example. Okay. So we're gonna move here. Now we need to basically determine is it linearly dependent or independent. Okay. So now let's create an augmented matrix. Okay. What we can see from here, we cannot determine is it linear dependent or independent by just looking at. Why? Because we have here we have 3 vectors and we have 3 rows in each vector, correct? So this is a problem, and we see that it is neither of the vectors is multiple of each other. Okay, now the third option to create augmented matrix, for example, 2 minus 6, 9, 4, minus 8. Oh, sorry, I forgot zeros here. Now, what we're gonna say, let's divide the last row by minus 6. We're gonna get 5, 7, 9, 0. We're gonna get, and let's divide the second row by 2. We're gonna get the following, correct? And let's divide, okay, for now, let's divide by minus 2. So it's gonna be 3, it's gonna be 4 here. Okay, now let's take the second row and reduce the third row. So we're gonna get times minus 3 and plus with this one. What we're gonna get? We're gonna get the following 5, 7, 9, 0, 1, 2, 0, 1, 2. And here is gonna be 0, 0. Minus 6 plus 4 is gonna be minus 2. Something like this, correct? So for now, it's not asked to reduce to the echelon form and so on and so forth. However, we can do that, okay? And let's take the last row and divide by minus 2. So here, by minus 2, okay? Divide by minus 2, we're gonna get 0, 0, 1, 0. And here, we're gonna get 0, 1, 2, 0, 5, 7, 9, 0. So let's take, so what we see? We see the following, that we have a pivot in each row, correct? Of course, we can reduce in the echelon form and so on and so forth by using this pivot, make it this element and this element to 0. We can then use this pivot, make it here 0, and so on and so forth, correct? But from here, as you have 3 pivots, correct? 3 pivots. It means what? It means that no free variables, right? Only basic variables. And therefore, what we say that our system is linearly independent. Independent. Now let's consider the second example. So I'm gonna write it here. Sorry. I'm gonna write it here. 0, 0, minus 3, 0, 0, 5, 4, 0, 2, minus 8, 1, and 0. Do you remember? So this is my 1 and this is 2, correct? Let me write it down, okay? We know that 3 basic operations, right? Replacement, scaling, and so on and so forth. So what you don't like here? Here I don't like that my third row is not in the right place. Now let's move it to the first place. Let the second row stay. And we'll basically interchange the first and the third row, okay? Now, without row reduction, what you say is you have a pivot in each row, right? There is no contradiction, nothing like that. Therefore, again, we say 3 pivots, no free variables, sorry for my writing. And we say that linearly independent. Okay, so basically that's it for today, guys. Thank you very much.